Hello, hello, and welcome back. Today we're leaving the two-dimensional world and exploring volume in the three-dimensional world using cross-sections. In this lesson, we'll use, calculus, of course, to find volumes of three-dimensional shapes where the cross-sections are geometric shapes like squares, triangles, semicircles, rectangles. We have so many options. Finding the formula for the area of the cross-section, well, that's the tricky part. But once you figure that out, then you can just integrate like you've been doing. You might see square cross-sections, or semicircle cross-sections, or triangular cross-sections. Let's just look at this middle guy for a second. It's a three-dimensional drawing, but you can kind of see through it, right? And you can see this semicircle that is a cross section of my drawing. Now, if you were to look at that just on a two-dimensional piece of paper, what you would see is just the bottom of this guy, like right here. Maybe something that looks like that. It's kind of weird, but I'll show you how it works. In general, everything revolves around the area of a cross-section in terms of its base. It's all about the base, which is the graph that you see in two dimensions. If the cross-sections are perpendicular to the x-axis, solve the equations for y. If the cross-sections are perpendicular to the y-axis, solve the equations for x. I will show you what that looks like in a second. For now, we're going to start with some sample area formulas where the area is in terms of the base. For example, the square here. It has a base of, b, okay? Which means that it also has a height of b. So the area of the square is going to be b squared. What about this rectangle here? It says we have a height of half the base. Well, let's label that. And we know that the area of a rectangle is base times height. So base times base over 2, that's going to be 1/2 base squared. Now the semicircle, that's interesting. The area of a circle in general is pi r squared. The area of a semicircle would be half that. And it's all about the radius, right? Well, if this semicircle has a diameter of b, its radius is just half that. The radius is going to be b divided by 2, and that's what needs to go into this formula right here. So the area of that semicircle is going to be 1/2 pi times b over 2 squared, or if you clean that up a little bit, then the area would be pi over 8 b squared. Remember special right triangles from geometry? They're very important and they're going to be very helpful for us today. Let's start by talking about the 45-45-90 triangle on the left here. It's got two legs, and let's say one of the legs is 1. Well, I automatically know that the other leg also has a length of 1. And using Pythagorean theorem, I know that the hypotenuse is the square root of 2. So that ratio is really important. 1, 1, square root 2. Now let's look at the 30-60-90 triangle. Start by looking at the leg that's across from the 30-degree angle. That's the short leg. And let's say it has a length of 1. Then I know that the hypotenuse has a length of 2, and I know that the long side across from 60 has a length of root 3. That root 3 is important for us today. Basically, if you take the short side, whatever the short side is, you can multiply that times root 3, and that's the long side. So let's try some sample area formulas with some triangles. First one, an isosceles right triangle with a leg as the base. An isosceles right triangle is a 45-45-90 triangle. And so if this leg right here has a length of b, then the other leg which is the height, also has a length of b. So the area is 1/2 base times height, or 1/2 b squared. Now, if I take that same triangle and turn it over so that its hypotenuse is the base, it's still a 45, 45, 90 triangle, but I need a height in order to find the area. So if I drop that height here, I've gotten now another little 45, 45, 90 triangle. And the base of just that little guy is 1/2 b. But that's really helpful because the height is the other leg of that 45, 45, 90 triangle. So the height is, well, 1/2 b. So back to looking at the whole triangle, if I want the area of it, I take 1/2 base times the height. So 1/4 b squared. Last one is the equilateral triangle. In an equilateral triangle, all the angles are 60 degrees. And again, in order to find the area of this triangle, I need a height. And this time, when I dropped that height, I created a 30, 60, 90 triangle. And so let's see, the base of just that little guy is 1/2 base. That's the short side. And the long side across from 60 is the height of my equilateral triangle, which is √3 times that. So back to my whole triangle here. I need 1/2 base times height. And so there we go, √3/4 b squared. The hardest part of this one is the height right there. Okay, so now is where it gets super fun. Find the volume of the solid whose base is bounded by the function y equals the square root of x, and x equals 4, and the x-axis. So right there. Each cross-section is a square taken perpendicular to the x-axis. That's important. All right, let me show you what this looks like. I've got cross-sections here, perpendicular to the x-axis, and if I tilt this, you can see that those cross-sections are squares. They're squares coming up out of the paper at you. Isn't that cool? And we can add more squares, and more squares, and more squares. And you can add an infinite number of squares to create this cool-looking solid here. And I can spin it for you, and you can see what it looks like. Isn't that cool? So that's what we need to find the volume of. How do we do that? So to begin this, I'm going to draw that pink line right there. And that pink line is the bottom of a square that's sticking up out of the paper at me. Now, the height of that pink line is the square root of x, because that's the height of the function there, which means the bottom of my square is also the square root of x. And since it's a square, I also know that that's the height. And if I want the area of that cross-section, the area of the square, well, it's base times height. So it's x. Now, if I want the volume of the solid, I want all of those squares. All of the squares starting from 0 and going all the way to 4, an infinite number. So that's an integral, 0 to 4, and then this right here, that's the area of the cross-section. So we can go ahead and integrate and evaluate that, and we get a volume of 8 units cubed. Okay, let's do the same thing, but change it up a little bit. This time, each cross-section is an isosceles right triangle with the leg as the base. So let's see what this one would look like. We'll tilt it for you. See, okay, there you can see the isosceles right triangles. The legs are the bases, and then if I add a bunch more triangles, now I get a different shape. Let's turn this so you can see it. So cool. So now we're going to find the volume of this one with triangles. An isosceles right triangle is the cross section. And again, if I draw the cross section on the two-dimensional space, that is the base of my isosceles right triangle, or the leg. It's got a height of, once again, root x. And this is a 45, 45, 90 triangle. So the height is also root x. So the area of that triangle is 1/2 base times height, or 1/2 x. And again, we want the triangles all the way from 0 to 4. So we integrate it. Here's my area, 1/2 x, integrated from 0 to 4. So we can integrate, evaluate, and this time it's 4 units cubed. Okay, what happens if they're equilateral triangles? This is a little bit harder, but again, this cross section here, the bottom here, that's the height of x, that corresponds to the base of my triangle. This is an equilateral triangle, so if I drop a height on there, the height is root 3 over 2 times the square root of x, and that's why we went through those sample area formulas earlier. So then the area of that triangle is 1/2 base times height, or root 3 over 4x, and integrate and evaluate. We can do all kinds of stuff with this. Let's try one more. This time, each cross section is a semicircle. Nifty. Okay, so there's my semicircle, and we've got root x here, corresponds to the bottom of the semicircle. But remember, the area is based on the radius. So if the diameter is root x, the radius is 1/2 root x. So here's the area of just a semicircle in general, and I've got to take my radius of 1/2 root x and plug that in. That looks awful, but if I clean it up, I get pi over 8x. And from 0 to 4, I can integrate and evaluate, and I get for this one pi units cubed. So pause the video if you need to write all this stuff down, or, take it in. Okay, we're going to change the game here a little bit. This says, set up an integral of the solid whose base is bounded by, two functions. 4 minus x squared, that's the top guy, 4 minus x squared, and x squared, that's the bottom guy. Each cross section is a square taken perpendicular to the x-axis. So what does this look like? Let's turn it for you. Whoa, so cool. Add a bunch of other squares here. There we go. You can see it filling in. Not crazy. We'll spin it so you can see it from some other perspectives. So cool. I think it kind of looks like an opera house, like a really nifty opera house. So how do we find the volume of the opera house? Well, let's talk about the cross sections here. Before, the cross section was just the height of the function, but this time it doesn't go all the way to the x-axis. It stops when it hits the other function. So we have to take the top function and subtract the bottom function from it. So 4 minus x squared minus x squared, 4 minus 2x squared. The cross sections are squares. That's nice. So we'll just take the area of that square, 4 minus 2x squared squared. And we just have to set up the integral this time. But the question is, what are the bounds of my integral going to be? Well, in order to figure that out, I would take the two equations, set them equal to each other, and solve for x. And if I do that, I've got, I get a negative root 2 on this side and a positive root 2 on that side. So those are the bounds of my integral, and I've set it up. Here's the area of my squares. Okay, last one, and of course we've got to Add a new dimension to this. Set up the integral of the solid whose base is bounded by the function of x squared plus 2, the y-axis, and the line y equals 6. Each cross section is an isosceles right triangle with the leg as the base. We've done that before. Taken, okay, perpendicular to the y-axis. That's what's different on that. We've got this function y equals x squared plus 2, but my cross sections are taken perpendicular to the y-axis, which means the height of the cross section has to be in terms of y, or it has to be an x equals. So this time, my isosceles triangle, the leg that's the base is going to be root y minus 2. So that's, we're talking about this. That height right there is root y minus 2. And then because it's an isosceles right triangle, that's the height of that triangle, 2. So the area is 1/2 base times height. And okay, what are the bounds of this one going to be? If I'm in terms of y, that means my bounds have to be y values. So we're going to go from 2 to 6 on that integral. And there we have it. These take some getting used to. They take some practice, but it's so cool what you end up with. So enjoy, good luck, and I'll see you next time.